So we're at hash day, so there should be a talk about, at least one talk about hashing. As you may know, I submitted a cryptographic function to the SHA competition and I did not win. So I will not talk about my function. I will talk about SHA in general, about the algorithm that won the competition, and I will finish with the exclusive announcement for hash days. So yes, you know, the function that won is called Keccak, K-E-C-C-A-K. If you Google this name, if you Google Keccak, you will find the hash function. If you Google Keccak, K-E-C-A-K, you will find this, which is a Balinese dance, and the picture behind is an example of Keccak dancer. So it's not an accident. The guys that designed Keccak, they added the C to avoid the confusion. They are not from Indonesia, they are not from Bali, they are Belgians. They have nothing to do with this dance, but they just thought that the name sounds nice. I asked them personally. Okay, so let's first go back to 2005, which is the origin of SHA-3, the origin of the SHA-3 competition. Why do we have a SHA-3 now in 2012? So it was mostly because a couple of years ago, there were the two papers that were published. Collisions for MD4, MD5, and collisions for SHA-1. So here's the message is, if you follow the blog of Bruce Schneier, he blogged that MD5 is broken, and then he blogged SHA-1 is broken. There's a big difference here, and you can probably guess what is the big difference between those two attacks. Would you like to use MD5 today? No. Do you use SHA-1? Yes. So the difference is that the attacks on MD5 are practical. It means that in this paper, they gave two examples of messages that gave an actual collision. So they could implement the attack, they could verify that it works. In the case of SHA-1, it's just theoretical. It means that they reduce the complexity of finding a collision. So in terms of complexity theory, SHA-1 is 160 bits of hashing, which means that you require approximately 2 to the 80 operations to find a collision due to the birthday paradox. 2 to the 80 is impractical for us, maybe practical for the NSA or other guys. But what they found is an attack that reduces its complexity to about 2 to the 67, let's say. It's not very clear, but it means that the attack is becoming more practical. Even though now 7 years later, we still don't have an attack on SHA-1. We still don't have an actual collision. That's why if you go to the e-banking webpage, the certificate is still signed with SHA-1. And the reason why we have SHA-3 is that NSA doesn't have much imagination. They design SHA-1 and then they design SHA-2, and the two looks very similar. And SHA-1 also looks like MD5. So they were concerned that the attack on MD5 that was extended to SHA-1 would one day become practical on SHA-1, and that it could eventually lead to attacks on SHA-2. SHA-2, which was published in 2002. Actually, it's a family of 4 functions, but this is the basic design. So of course we panicked. NSA panicked. NIST, the standardization organization of the US, was panicking, and cryptographers were not panicking because it meant a lot of work for them. It means new papers, new publications. So we were actually quite happy with this bad situation. In 2007, NIST published in the Federal Register, so which is the official journal of the US government, a call for submissions to SHA-3, which essentially means that it was like for the AES encryption algorithm, the new algorithm SHA-3 would be selected as a public competition. Anyone could submit a design, and then NIST will pick the best one, well, the one that they deem the best, at least. So what were the criteria? What were the requirements in terms of engineering? Well, it was not like, well, I don't know if you're familiar with requirement documents, which are very strict, with very strict terminology. This was not like this. It was much more vague. They said, for example, well, the new hash algorithm will augment and revise Philippe's 18002, which is SHA-1 and SHA-2. So in other words, SHA-3 is not intended to replace SHA-2. It will augment it, whatever it means. So we have SHA-2 here. SHA-3 will not replace it. It will be something different, but a bit better. It will augment the standard. Now in terms of security and performance, so the security strength should be at least as good as that of SHA-2. So how do you measure security of a cipher, of a cryptographic algorithm? Well, you can't. You have no single metric to say this has security of 42.813 bits. We just don't know how to do it. We just use a heuristic based on the number of rounds attacked by cryptanalysts. And we have what we call a security margin. For example, in AES, there was an attack when it was published on 6 rounds out of 10. So we had a security margin of 10 minus 6 equal 4 rounds. Then we run into the problem of what is an attack. It is something that you can implement. It is something that is better than what you would expect ideally. It's extremely unclear. And the last point is that this security should be achieved with significantly improved efficiency. It's a bit better easier to define because you just measure the speed and you see how fast it is. But you have several dimensions in terms of efficiency. What platform? Is it a 64-bit Intel CPU? Is it a 32-bit ARM processor? Is it an 8-bit AVR? Is it an ASIC, an FPGA, an FPGA? Is it the amount of memory that your implementation will consume in a microcontroller? So it's also quite not easy to define. Okay. So a year later, in November 2008, they received 64 submissions. Only 51 were what they called complete and proper, which means that 13 were not complete in the sense that the specification was not readable, was ambiguous, or that the submitter forgot to send test vectors, or well, 13 were complete crap. And in 2009, they selected 14 of them in the second round of the competition. So in the 51, there were many weak submissions, many not so serious submissions. Many of them were broken. Many were obviously too slow or too big. So we ended up with 14 reasonable hash functions. And in 2011, or no, in fall 2010, 5 arrived in the final. But here, it's not because the other were broken, but just because they were deemed a bit more secure or faster. So the submissions came from this, well, it's not an exhaustive representation, but you see that we have guys from industry, names as Sony, Microsoft, Cerdicom, IBM, academia, EPF in Switzerland, things in Israel, in Austria, in France, also government institutions, Syndia in the US, we have also the people from the French ANSI. So a very wide spectrum of submitters. And it's, yeah, the Motion Derby, we put all those guys in a room and we try to beat on the head of each other, and at the end, nitpick ones. So you see, it's a very nice strategy for this because it's just free work. They organize this, they submit your thing, break the designs of the others, implement them, and at the end, we will pick the one that is the best. So it's work worth millions of dollars because, well, mostly paid by academia, which means paid by, well, by you, by taxpayers. I have to say that when designing Blake, I was doing my PhD not very far from him here in a Fachhochschule, and I was supported by the National Swiss Foundation for Science, which is your money if you're Swiss. So sorry. So it was about the work during those 4 years were about security evaluation and performance evaluation. And maybe one success of SHA-3, if not the winner, is all the work that's been done in those two sides, security and performance evaluation. This is an example of a table of the weak hash function that have been broken. Red means that you have an actual collision. Orange means that the attack is not practical, but it's on the verge of practicality. So I will explain in detail what it means. No, just kidding. But just to say that this competition gave rise to extremely sophisticated and maybe over-sophisticated cryptanalysis techniques, in the sense that we came up with very artificial things like in hash functions, you say breaking hash function is finding collision, inverting the function. We came up with notions of what we call distinguisher, which means distinguishing the function from a random oracle, which is an abstract mathematical object which is fully perfect. And yeah, we were in this bubble of research, and most of them sometimes it doesn't make sense, but see, it's good for researchers because they get more papers, they get a longer CV. Well, you know the game. Yes, things like these big leak attacks. So this is the attack that broke AES. Maybe if you read the news 2 years ago, they said that AES is broken. So AES is broken for academics, but not in reality. But they got a paper at the crypto conference. So maybe more interesting is the performance evaluation. Lots of extremely competent people worked on this. For example, ETH, the hardware group at ETH, worked with GMU in the US, George Mason University. They fabricated an actual chip where they implemented the 5 finalists, 2 architectures for each finalist. They did this project called Athena. It's a framework for automated testing of FPGA implementation. You give for each function a number of VHDL implementation, and on a number of FPGA devices, it will test different synthesis options, and it will automatically report the best performance figures to give you a comprehensive performance overview of each function. Maybe even better in software. Probably you know Dan Bernstein, which is the author of QML, DGB-DNS, lots of things, lots of very good crypto and security work. He did this thing called SuperCop. It's even crazier than what I explained before. It's about software performance evaluation of hash functions. It's a framework that collects C or assembly implementations of hash functions. So for each of the candidates in SHA-3, he collected all the implementations available. Everyone could submit a new implementation. And for each machine on which you run this program, the program will test all the compilers that you have, for example, GCC, ICC, Visual C, with a bunch of different compilation options. So minus O3, minus omit frame pointer, blah, blah, blah. All these different combinations. And at the end of the day, it will report the single fastest combination. And the goal is to really have a meaningful value of this is how fast is my function. So of course, it's just as fast as the best implementation that you have, but it's maybe close to the best that we can do. So this gives you an overview. This is on a 64-bit architecture, Sandy Bridge, not the most recent Intel architecture, microarchitecture, but the previous one, where you have the AVX instructions and AES instructions. You see that the fastest is Blake 512, which means the submission Blake with 512-bit output. Skane, the submission of Bruce-Nair, Ernest Ferguson, and his friends is a bit slower. This is a log scale, by the way. And here we have SHA-2, SHA-256, SHA-512. So we have this kind of graphs. And this is a Sandy Bridge CPU, previous generations of Intel. So you see, we already have a comprehensive view of the performance of each function on each platform, and this is the single best implementation. We could go on, this is the AMD K10, AMD Bulldozer, which is the recent desktop architecture, Bobcat, it's AMD's mobile macro architecture, this is Intel. We can have Power PCs, mobile processors, Atom Eden. Scorpion is Qualcomm Snapdragon chip that you have, for example, in some version of Galaxy S2 smartphones. This ARM Cortex A8, A9. So you see we have big performance discrepancies from one platform to another. Here it's mostly due to the fact that, for example, on Tegra 2 ARM, you have only 32-bit registers, 32-bit instructions. In this Cortex, it's a 32-bit ARM, but you have the Neon extensions that allow you to do 64-bit instructions. Okay, so I won't enter the details, but well, you get the idea. And this is for microcontrollers, Atmel chip, MIPS things. I don't know why is this one, but yeah, a large diversity of platforms. So, and this was not done for the ES competition. This is unique for SHA-3, and it's not proper to SHA-3. This can be used for the next cryptographic competitions, and it's not just about hash functions, but also block ciphers, stream ciphers, authenticated protocols, anything. Okay, so now in 2012, today, we had those 5 candidates. Blake, which was myself, Professor Willemeyer from the Fachhochschule Norwegen-Schweiz, Luca Hensen from ETH, now UBS, and Raphael Pan from the UK. This one is mostly by academics from Austria and Denmark. JH is a guy from Singapore University. Ketchak, Johan Dem and his friends from Belgium, ST and XP. And Skane, US guys mostly, so I said Bruce Nair, John Callas, Nils Ferguson, Yoshi Kono, so quite famous names. Yeah, Nadian, they won. One detail is, so the lead designer of Ketchak is Jon Demmen, and if this name rings a bell to you, it's maybe because he was also the main designer of AES. So it's not fair, but Belgium wins twice. I thought that being Swiss neutral would be an advantage, but so maybe if you remember the slides before, we had that Blake and Skane were considerably faster than SHA-2, whereas Ketchak is here, for example, twice slower than SHA-512. So it may seem a bit surprising why a function slower than SHA-2 won when we had faster functions. So it's been not that simple. So why did they choose Ketchak? So in the press release, they explained that they chose it for its elegant design. Okay. Large security margin, which is true, but which is true for all the 5 finalists. Good general performance, and excellent efficiency in hardware. And it is extremely fast, extremely flexible in hardware. Hardware means ASIC and or FPGA. And for its flexibility, which is a bit a fuzzier notion, but it essentially means that if you have to implement it in hardware, you have different architectures, different trade-offs between space and time. And another reason said it complements the existing SHA-2 family. In other words, that it's extremely different from SHA-2. And I think that makes sense, because if you look at Blake and Skane, which are much faster than SHA-2, they are not similar to SHA-2, but they have more similarities than Ketchak does. So being similar to SHA-2 doesn't mean that it will be broken by the same attack, but I don't know, maybe NIST is working with NSA, maybe they have their reasons. And indeed, they say that an attack that could work on SHA-2 most likely will not work on Ketchak, because the two are designed so differently. Well, so I think that applies to all 4 candidates. And yes, it's essential insurance. But I think the most relevant argument is the hardware efficiency. So here, how Ketchak works. I don't know if you already implemented SHA-2 or MD5 or SHA-1, but you know it's a hash function, but it's not a single algorithm. It's composed of a compression function that takes blocks of message, blocks of 512 bits for SHA-1, for example, that takes this as input, that takes an internal state, and that maps those 2 values to a new internal state. In other words, it takes big data and it compresses it to a smaller amount of data. So it's called a compression function. And in the case of Ketchak, we don't have such a compression function. We only use a permutation, which means that a function that is invertible. You can go from the start to the end and the other way around. So this sounds a bit surprising, because we're talking about hash functions, which are also known as one-way function. And if a function can be inverted, it's not one-way. So here, the fact that the iteration function is not one-way does not imply that the whole function is not one-way. So how does it work? You start from an initial state set to 0. For Ketchak, it's 1,600 bits. You may compare this to the state of SHA-512, which is 512 bits. So here is your message. They call it PAD because it's the padded message. Padded means handing, traying zeros. So you split your message in blocks, and you XOR the first block to the internal state. You apply the permutation. You end up with a new state of the same size. You XOR the subsequent message block, and so on and so forth. And when you have XORed all the message blocks to the state and interleave this with permutations, then you enter what they call the squeezing phase, because it's a sponge function, which was invented by the same guys. So once you have absorbed all the message, you run this permutation again and you extract chunks of internal state. So in other words, it never leaks the whole state, but just a small part of it. And what they proved mathematically is that if you are given those small chunks of state, if this function is good, then you cannot invert it. And I think that's a pretty good idea because it's extremely simple. You just have this to implement, and I think it's reasonable to say that it's simpler than the construction of SHA-2. Okay, so here's for the details of the function. So this is what is inside F. That sounds a bit scary. You have all these Greek letters, so I don't know why Johan uses the syntax with theta, rho, p, key. So I want to explain what it does, but just to give you an idea that it does something quite thoughtful. They didn't do this at random. There are good reasons why they do those operations, those matrix transpositions, those blah, blah, blah. And if you have to implement this, I don't think you should start from these specs, but this is the equivalent representation, which is much easier. You have a couple of byte arrays, C, D, A, B, and you just do XORs, rotation, word rotation, and that's it. So if you know a bit about cryptanalysis, you know that if you only do XORs, it's very bad news because it's completely linear. If you only do XORs, you can essentially invert the function. You can guess all the details without knowing what the function is doing. But if you look carefully, there's not only XORs, or there's the rotation, but it's just moving the wires all around. There is this not an end, logical end. So this adds a nonlinearity. The function describing the round function doesn't have degree 1, but degree 2. It means it's an algebraic function. And if you repeat it several times, the algebraic degree will grow exponentially. In other words, in terms of cryptanalysis, it will be secure. In other words, resistant to differential or linear cryptanalysis. Without this end, if you implement it and you mistakenly made an XOR here instead of an AND, it becomes totally insecure. So be careful when you write the code. And of course, do not write this code because the function will be extremely slow. You should do this instead. They have developed complex techniques to optimize implementations. So if you don't want to implement it by yourself, you can go to this to another address where you can get the C code, the assembly code. But yeah, on the one hand, it's simple to describe. Well, not so simple. But if you have to implement it efficiently, it becomes much more tricky. But it's doable if you care about speed. Okay. So this is how fast GetShack is on an example of an Intel Core i5. So this version is a Sandy Bridge processor. You have the AVX instructions running at close to 3 GHz. This is how SHA-2 is, how fast SHA-2 is. This is the 256 and 512-bit versions. The megabytes per second figures. So we said GetShack 256 is faster than SHA-256. On the other hand, the 512 big version, the big version is considerably slower. And just this is my function, which is faster and not fast enough. Sorry. So you have similar comparison if you move from Intel to AMD. This is the FX 8120 bulldozer microarchitecture. It's a bit different, but you have the same comparisons. This the small GetShack is faster than the small SHA-2. The big GetShack is slower than the big SHA-2, and so we are a bit slower than GetShack, interestingly. But it's because of features of the bulldozer architecture, where you have more efficient word rotations due to the XOP instruction set of AMD. And again, the fastest one is Blake 512. Now if you go to another type of platform, ARM, this is the Snapdragon S3 of Qualcomm. So it's a very nice ARM-based system on chip. So here SHA-2 is very fast, and even faster than Blake. One of the reasons is the memory consumption of SHA-2, which uses a small internal state, and this means, to make a long story short, fewer load and store operations, which slows down Blake a little bit. And here you see that well, you don't want to use the big HSACs if you care about speed. Well, and then I'm not sure that you really care about speed on smartphones. And maybe I guess that in the future system on chips, you will have hardware accelerators for SHA-3 if SHA-3 is ever used. Now, if you look at the very low end, this is an AVR Atmel microcontroller. So here you have 2 log scales, the throughput. So higher means faster. Here the memory consumption, and you have different implementation. So each dot is an implementation. So the red line here is Blake 256. We have a version here that consumes fewer than 4 kilobytes and is reasonably fast. Grostel is tied with Blake here. Now the smaller version, interestingly, is KitSAC. So about 2 kilobytes, about 2 kilobytes, and it's about 4 times slower than Blake. But again, you have to be careful with this kind of figure, because you have to ask yourself, what speed do you need on an AVR? Will you hash 2 gigabyte files on your microcontroller? Well, I don't think so. So maybe on this kind of platform, the most important is memory consumption and not speed. This is a MIPS, a TI MIPS chip. Here a bit different comparison. So again, KitSAC is the fastest, but Blake is about as small as KitSAC, but is a bit faster. And the speed is 8 bytes. What does it mean? 8 bytes by 1000 cycles. Well, don't care about the unit, just compare the functions. So you see that on those 2 chips, KitSAC does fairly well in terms of speed, and is extremely small. So interestingly, KitSAC is very good on the low end, not so good on the high-end CPUs, but in most applications, SHA-2 is fast enough. Unless you are in an application where you really care about speed, you really need the high speed, but don't forget that you are limited by the hard drive write speed. Even though SSDs have speed like 450 megabytes per second, it's still lower than the write speed of most recent SSDs, for example. Okay, now in hardware, so another complex figure. So here you have the area, so smaller is better, and here the speed. So in the other direction, so the more you are at the left, the better it is. And you see that KitSAC is extremely good here. It's one of the smallest, so you have different architectures, again, different hardware architectures. It's one of the smallest. SHA-2 is a bit smaller, but KitSAC is much faster than SHA-2. And if you look at the unit, it's more than 15 gigabits per second on this platform, which is a UMC technology on 180 nanometers. Whereas KitSAC tops at more than 5 gigabits per second. So again, the question is, do you need this extremely high speed? I guess there are some applications where you need this high speed. For example, if you have I don't know, appliances for doing security monitoring, and you need to hash all the binaries that go through the network, you will probably care about speed here. But again, this is on long messages. If you have short messages, you have a notable overhead. If you hash only 8 bytes or 16 bytes, you won't have this performance unless you do appropriate pipelining and prioritization. On FPGA, it's a bit different. FPGA is a different beast than an ASIC. And here, the throughput is there. The higher the better. And this is the area, so the opposite of the previous graph. Here we see that one of the smallest hash function is skein, JH, Blake, and KitSAC in FPGA is bigger than Blake, and bigger than SHA-2 too. Quite strange. And if you look at the throughput, the speed, Ketchak is very slow on this FPGA, and Blake is the fastest. So you see that you cannot say, well, this function is the best in hardware because we have very different comparisons in ASIC and in FPGA. Okay, still have some time left. So I said that Ketchak is good in hardware, but mostly in ASIC, in a dedicated circuit. Now what about security of Ketchak? So they were very clever because they put cryptographic prizes, which means that let's say in 2 months we will give a crate of Belgian Trappist beers to the authors of the best attack on Ketchak. And with my friend Dima, we won a crate of all Trappist beers, including the Westfletteren, which is very difficult to get. So they repeated this several times with an Italian coffee machine. One of the authors, Guido, is Italian. I think that's handed, well, I don't remember, but they gave 3 or 4 cryptographic prizes as an incentive to attack the function. And as conclusion, the function was not attacked in the sense that you security guys think that attack mean an actual threat. They were just academic attacks on reduced version. For example, the round function of Ketchak is 24 rounds. Initially, it had 18 rounds, and they increased from 18 to 24 because there was a totally crazy attack on 17 rounds. This was maybe more about publicity than actual security. So an example of attack that you can see in research papers is this unaligned rebound attack. You don't want to know what it means, but they have an 8-round distinguisher with 2 to the 40, 491, to give you an idea, since the amount of electrons on Earth is below 2 to the 100. The AES key is 128 bits, so which means 2 to the 128 to attack, and you can essentially read this as impossible. But you get a publication because this number is smaller than 512, so it's better. Some attacks that do work on a PC, on a single PC within a few minutes. Collisions, something meaningful in standard Ketchak, which are reduced version of Ketchak, with 4 rounds out of 24. So when we speak of security margin, so that we have like 20 rounds to break to reach the full version. And another one is my favorite one. It's a zero-sum distinguisher. It's something completely stupid that means absolutely nothing. And I can't say bad thing about this technique because I invented it. It essentially means that you find a number of inputs that if you XOR all of them, you get the 0 string. And for all those inputs, you get all the respective outputs. You XOR all the outputs all together, and you get 0 as well. It doesn't look like an attack at all, but this should not work on an ideal function. And yeah, I initially published this to attack Ketchak, or to attack Ketchak. And here the complexity is 2 to the 1579. But it's an attack because ideally it would be 1590. And these 2 Chinese guys are happy because they had a publication in a conference, so they could travel to a remote place to present their paper. Okay. One real advantage of Ketchak is that you can do this. H, the hash function, K, key, M, message. You hash the key followed by the message, and you get something. And this is equivalent to HMAC. This is a keyed hash function, which is used for HMAC for message authentication codes. But it's not secure with SHA-2, because with SHA-2, if you get this value, then you can create the value of K, M1, and followed by M2 without knowing K. In other words, don't do this with SHA-2, but with SHA-3 you can do it. A not so nice property is that if you are in an attack model where the full state can leak to the adversary, then as I explained before, it's not one way, you can invert it. So if you know the full internal state, you can go backwards up to the initial state, and the initial state is essentially the key. It's a bit an artificial attack model, but I know some applications where it's realistic. So should we care? Should you care about SHA-3 if you are developing a product? Should you implement SHA-3? Should you use SHA-3 in your applications? Well, let's say what NIST is saying. This is an informal comment by John Kelsey from NIST. He say, we're not telling people to move from SHA-2 to SHA-3. The two standards will coexist. Is that if you really need extremely fast hashing in ASIC, then you can use SHA-3, and you will still be compliant with the NIST standard. Because in many applications you have to use standard because your clients want you to use standards. But for general purpose applications, there is no problem with still using SHA-2. And one advantage of KETSAC is you can use it for different applications than hashing. You can use it for encrypting, for message authenticated code, like I said before, and authenticated encryption. It's not a standard, it will not be standardized by NIST, but the advantage is that in your chip, in your software, you just have to implement this function, and you get for free MAC, RNG, cipher, and hash function, of course. Just the rough idea is that you not only XOR things to the state, you also extract things at the same time that you XOR data to the state. So you can look at the specs for more details. And you can't directly do this for the other finalists. So now what about Blake, which is the function as submitted? Yes. Yes. Yeah. The zero-sum property applies individually to the function f, but not to the hash function as a whole. And anyway, it has this crazy complexity that you can just ignore it. So Blake, so many people told me, yeah, you will win SHA-3, you're faster on embedded system, you're faster on 64-bit, you're easier to implement. And well, we did not win, but a colleague of mine told me, yeah, but Blake will be the Ksenia Chumicheva of crypto. Because I don't know if you know this lady, if you're not Swiss. So this pretty girl participated to the national beauty pageant in Switzerland. She did not win, she was second or third, but she was much more successful than the winner. She had some other advantages besides this. And so I hope that Blake, well, we may not be as successful as Xenia, but we are working hard to improve Blake, and because it was originally an academic work, and unfortunately, academia is often disconnected to the real world needs. So we are now working with a bunch of people developing things like cloud storage products, developing all kind of applications, and telling us what they want for a hash function, what is overkill, what is over-engineer, and what kind of cryptographic functions they would like to see for users, for developers, for implementers, because implementers don't care about zero-sum distinguishers, don't care about security proof, they care about the time it takes to implement it. So there will be a Blake 2. It's coming soon, and I can already tell you that this will be good for cloud storage integrity check, for data applications, maybe for HIDS, no, I'm not sure, for P2P. That's why in P2P, Tiger is still used, and MD5 is always used in IDS. There will Blake 2, I don't know when, but probably this year, and you will hear about it if you follow my Twitter account. And I would like to thank you for your attention. And